Hello and welcome to Gaffy's Grinds. This is our first video in our chapter on acids and bases. If you're new to the channel, I always ask for a few things when we get started, and that is to make sure that you are listening to me when I'm explaining things. So the best way to do this is to turn off anything that might distract you. That includes your social media tabs. If you've got them open your computer, your phone, try and turn it off or put it somewhere where it can't distract you. And make sure that you take the opportunity to do the practice questions that I give you. If you don't do them, you're not going to learn very much from watching these videos. This is what makes this channel different, is that you get a lot of practice and you get an opportunity to master content before we move from one step to the next. Before we begin and jump in and look at what acids and bases are, we're going to look at a couple of chemical reactions involving them. So what I want you to do during this reaction or during this video is I'm going to be talking about what's going on. What I want you to do is I want you to think about what exactly is going on in the video that tells you a chemical reaction is happening. So think about being able to describe what you've seen. All right, so let's go ahead and play the video and we'll watch what goes on. Now, I'm not going to try and not watch all of it. It's only some of it is important. So let's give it an opportunity to load up here. And I'm going to zoom in a little bit more. All right, so I'm just going to skip past some of this stuff that I don't really want to discuss. Okay, so there's a bit of a build up here and then, okay, just go back here. So here we see we've got two cans. They are Coke cans, and we're going to put some chemicals in. As you can see, some liquid chemicals going into the cans. It tells you what they are there. We'll discuss what type of chemicals they are in a second, but more importantly, I want you to watch what exactly is happening that's telling you a chemical reaction is happening. All right, so you can speak your answers out to the screen now. Is there anything that's going on that tells you a chemical reaction is happening? So what I see is I see fizzing, I see bubbling, I see steam. So hopefully you saw them things too. The steam is suggesting heat. The bubbles are suggesting that a gas is forming. If a gas is forming, that's usually a good sign that there's a new substance being formed. We put in a liquid, something happened, you got fizzing, showing the production of a gas. Most importantly, what's happening to the structure of the metal can? Metal cans are made of aluminium, and we could certainly say that they are breaking down or they are being eaten away. They're basically reacting and turning into a new substance. The aluminium is not aluminium anymore. All right, don't mind the Pepsi can. They just talked a little bit about why it doesn't work in a Pepsi can. Pepsi cans are made of a different metal, so it doesn't react with these two chemicals. Now, Coke cans are not easy to destroy. If we left a Coke can to rot, as you can see, all that's left really is the plastic, the outside. If we left a Coke can to rot out in the garden, it would take hundreds and hundreds of years for it to do anything. It could stay there, rust away a little bit, but it's going to take a long time for it to do anything. Whereas here you can destroy it in a matter of seconds. Now that's not an easy thing to do, to destroy a Coke can. You can find litter cans around for years and years. It's surprising then how easy it is for this chemical reaction to do it. That's where this symbol comes in. This symbol right here. You've probably seen it before on some chemicals. And what it means is, it means that if you spill it on certain materials, it reacts so violently that it burns through them. So it's basically going to react very quickly and very violently with chemicals, and it essentially means that they decay. So this symbol here means corrosive. Corrosive. And it's a hazard that we associate with acids and bases. Acids and bases, which are the subject of these common videos, are corrosive. So if we're often asked about what hazard is associated with acids and bases, and you've got to really focus in on this symbol now and see what's going on. We've got some test tubes with liquids. We're pouring them on different surfaces. We've got a hand, and we've got like a surface that might be wood or it might be stone or something like that. And it's kind of showing that they're burning or decaying. It's kind of digging and burning a little hole in them. And some acids are extremely corrosive, other ones not so much, but definitely a hazard associated with these particular chemicals are acids and bases. Now they they do give us some wonderful chemistry, so we don't want to, like, you know, even though some of them are necessarily not that safe to be messing around with, as long as we use the proper precautions, we do want to use them in industry, in chemistry. We want to use them because they give us some wonderful chemical reactions. They're not all particularly dangerous. It just depends on how corrosive they are. So more corrosive things are more dangerous. So again, they come with a bigger warning. You've got to wear more personal protective equipment like goggles and gloves, where some acids are even safe to eat. So that's what we're going to get into. But just a quick introduction that we would find this particular hazard associated with acids and bases, or acids and alkalis. Okay, so now where do I want to go? 1 second, just pause the video for a sec. Okay, so now that we know that acids and bases are corrosive, let's look at what acids and bases, or acids and alkalis, actually are. So what are acids and alkalis? Well, it helps to begin with looking at some things, some everyday things that might come under the labels of acids and alkalis. So one thing that we might use fairly often is, here's a bottle, and in the bottle is this stuff called vinegar. Vinegar has a distinct smell. We put it on chips. Vinegar is an everyday example of a substance that is an acid or is acidic. This here can of Coca-Cola is another example of an acid. Here are some fruits. We've got things like lemons. That's not a great lemon, but you get the idea. It's a lemon. And we also have things like oranges. These are examples of everyday acids. They have acids in them. Batteries tend to work on acids, particularly car batteries. So this is batteries. And we also would find acid for anyone studying biology. We'll find acid in the bag at the bottom of your esophagus that we call the stomach. So all of these are examples of everyday acids. So what do we call these acids? Well, obviously they've got a name. Just going to actually move this, give myself a bit more space. Okay, so the name of the vinegar, or the acid that we would find in vinegar, is this acid called ethanoic acid. Ethanoic acid. And it's obviously quite safe. So in terms of corrosiveness, think about, is it going to be highly corrosive or not highly corrosive? Think about what we can do with it. We can basically eat it, and we put it on our chips, so it can't be overly corrosive. Cola is another example of an acid. Generally, any carbonated drinks, any fizzy drinks, fizzy stuff is going to have this stuff called carbonic acid. Citrus fruits, that's why they're called citrus fruits. Oranges and lemons, they've got this acid called citric acid, where they get their name, citrus fruits. Battery acids is a very strong acid, very corrosive acid called sulfuric acid. And in the stomach, we find a very common acid called hydrochloric acid. So these are everyday examples of acids. What about these other group of chemicals? These chemicals called alkalis. Alkalis. Well, alkalis we find in things like bleach, used in the toilets. We find them in other cleaning products as well. Many cleaning products and detergents for cleaning foods and cleaning countertops and stuff like that are alkalis. Cleaning products. Fertilizers that we use in farming tend to be alkalis, and things like toothpaste tend to be alkalis. Toothpaste. Why should toothpaste be an alkali? Well, many of our foods, like we see over here, citric acid, vinegar, cola, many of these are acidic. And if we leave acidic conditions in our mouth overnight or for a long time, we don't brush in between, you can imagine what's happening there. It's changing the acidity of your mouth, making it more acidic. What does that do? That makes it corrosive. And what's going to get corroded? Only your teeth. So there are some everyday examples of acids and alkalis. All right, so you're ready to answer some questions now. All right, so I'm going to show you the questions. I want you to pause the video and I want you to answer these questions for me. So here we go. From memory now, what I want you to do is pause the video and answer these questions. All right, so a reminder then, you should only be watching the video if you pause the video and you answer the questions. If you're not going to do these, you're wasting your time. So you don't, question 2 and question 3 ask you for 3 examples. That's plenty. Okay, if you can remember that. All right, so let's have a look at the answers. So pause the video and make corrections to your answers now, please. All right, so it's really important that you do actually correct your work and you go through the process of giving yourself the confidence that you got them right. And if you didn't get them right, not a problem, mark it wrong and to make sure you take down some answers that are correct. We don't want to leave ourselves with the impression of an incorrect answer. All right, so these are everyday acids and bases that we find in products that we can buy in the shop and we can buy at home. What exactly is an acid then? Why are they acidic? Okay, we're going to look at first of all, we're going to look at some common acids that chemists would use. So not just our food, the acids and stuff we can buy in the shop, stuff that we can buy chemically wise. So we're going to look at what we call common acids, or sometimes these are referred to as common lab acids. Okay, so some common acids are hydrochloric acid. This is probably the most common one you ever hear of. It's the most common one we meet on our course. It's got the symbol or chemical formula of HCl. So it's made of a hydrogen atom and a chlorine atom. And I'm going to put this little thing afterwards, AQ, and that means aqueous. That means it's HCl, and aqueous means it's dissolved in water. So hydrochloric acid is our most common laboratory acid, HCl. Another acid that we come across in leaving cert chemistry is nitric acid. This tends to be a very corrosive acid, and it's got the formula HNO3. HNO3 is nitric acid. And obviously that is also it's not obvious I suppose, but it's also AQ. AQ for aqueous means dissolved in water. And lastly, another very common one is sulfuric acid. This is the same acid that we found earlier in batteries, sulfuric acid, but we use the pure form of it in the lab in chemistry. Its formula is H2SO4. AQ for aqueous means dissolved in water. So that's sulfuric acid. So why then are these acids? What exactly do they do that makes them behave like acids? So why are these acids? A reminder, if you're new to the channel, if you listen while I speak, don't try and write everything down. I mean, you can go back and take it down after if you want. Most of the questions ask you to write it down anyway. It's much better if you listen while I speak and then answer the questions. Otherwise, if you're listening while I'm speaking, you're not really learning the things I'm saying. All right, so why are these acids? Well, the reason why they're acids is if we take a beaker of water and we fill it up. So this is a beaker and this here is water. I'll draw it blue to symbolize that it's water. Okay, so we've got some H2O. This is water and this is obviously a liquid, L for liquid, H2O. We took our H2O, we put it in the water. Now, let's say we take our example of our chemical of HCl, hydrogen chloride. This is actually a gas, this substance. Hydrogen chloride is a gas. If we take that hydrogen chloride and we pump it into the water, we say we dissolve the gas in the water. So we dissolve it in the water. HCl, if we were to look at it, is made of a hydrogen atom like this, chemically bonded with a chlorine atom like this. But when we put it in the water, what happens is it splits into a H plus ion and a Cl minus ion. And obviously, there's not just one atom or one molecule of HCl. This would happen with, if we pump some gas in, there'd be millions of them doing this. And they split into a hydrogen ion and a chlorine ion. So this is an ionic substance splitting from a hydrogen chloride into hydrogen ion and chlorine ion. We call this splitting dissociation. Dissociation. So it's kind of like these are associated with each other, and these are dissociated with each other. Dissociation. In other words, they stop being associated with each other. They stop sticking together. So when they dissolve, they dissociate. The ions separate. They spread out. We can write a little equation that can help us explain what's going on. A HCl is basically turning into H plus Cl minus. That's what's going on. And this here is a gas. These two are aqueous because they are dissolved. So we go from HCl to H plus aqueous, Cl minus aqueous. Now, why is it that these are acids then? Well, it is these excess H plus ions, when they're dissolved in water, dissolved in water, makes a substance acidic. Okay, so these excess H plus ions dissolved in water is what makes a substance acidic. So if a substance can split up to give these extra H plus ions, this is what makes a substance acidic. If a substance doesn't produce these guys, then it can't be acidic. But if a substance splits up and gives loads of extra H plus ions in the water, it's going to be an acidic substance. And there's different types of acidic substances. Some substances, when we put them in water, give a few H plus ions. And some substances, when we put them in water, give a lot more H plus ions. We would say this one is less acidic. This one is more acidic. So it's the level of H plus ions in the water that makes it more acidic or less acidic. All right, ready to do some questions on acids now. Okay, so let's take a look here at these questions. Okay, so I want you to do questions 1 to 6 here. All right, so pausing the video and doing these questions, please. All right, so you should only be watching the video if you have done these. Okay, so a reminder then that you won't learn anything, you won't learn anywhere near as much if you don't do the questions. All right, let's have a look. What have we done here? From memory, list 2 common lab acids. So you could have had hydrochloric, you could have had nitric, you could have had sulfuric. So well done if you got any 2 of those. From memory, again, ideally, this is why I don't ask you to write stuff down and then copy it. You don't learn anything by doing that. We learn it by seeing, can we retrieve it properly? Which diagram shows an acid, A or B? Okay, so hopefully you went with A. Hopefully you went with A. A shows an acid, B does not show an acid. How do you know? Well, the reason why I know is because A produces excess H plus ions. So if you said that, well done. Here they are here. A produces H plus ions. B does not produce any H plus ions. Both diagrams show ions which have separated when mixed with water. What word describes this? So as you can see, ions, we've got separate ions. We've got H plus and Cl minus ions, which are separate. And in the second one, we've got Na plus ions and OH minus ions, which are separate. What word describes this? That would be dissociated. Say the ions are dissociated. Well done if you said that. Which of these containers would be more corrosive, A or B? Okay, so I'm hoping that you said B. And if you said B, well done. And then number 6 asked, how do you know? So how is it that we know that B is more corrosive? Well, B has more excess H plus ions. All right, so again, well done if you got all of those right up to here. Okay, what about some alkalis then? Let's look at some common alkalis. So we've already looked at some everyday alkalis that we find in cleaning products and stuff. What about common lab alkalis? All right, so common lab alkalis that we will have maybe heard of before. The first one and the most common one we come across is this subchemical called sodium hydroxide. We often find this, it's the main ingredient in oven cleaner, but it's also the main ingredient in, like, it's the main chemical in some of the titrations that you do in leave insert is sodium hydroxide. It's got chemical formula NaOH, sodium and oxygen and a hydrogen. Sodium hydroxide, that is the first common lab alkali. Another one that we come across is the substance potassium hydroxide. Potassium hydroxide. And that's equal to K for potassium and OH, potassium hydroxide. Another one is calcium hydroxide. And you might be spotting a pattern at this stage. Calcium hydroxide is CaOH2, like that in brackets. So 2 OHs stuck to a calcium. Right, so what is it then? Why are these alkalis? What makes these alkalis? So why are these alkalis? And you'll be glad to know that it's a similar idea to why the first ones were acids. So we'll take our container again, and in our container, we're going to put water. So you'll notice that water is really important here. Water is necessary for things to be acidic or alkaline. Okay, so we take our water and we put it into a beaker or any container. This is our H2O, which of course is a liquid. H2O liquid, L for liquid. Take our water, put it in the container. We're going to take one of these chemicals now. Let's take our example, NaOH, sodium hydroxide. And sodium hydroxide is a solid. It comes in these little pellets. So we take our sodium hydroxide and we put it in the water and we dissolve it. Now, what does sodium hydroxide look like? Sodium hydroxide looks like this. An Na atom, or an Na ion, and an OH ion, like this. And here they are associated, just means they're connected. But when we put them in the water, they make this, Na plus and OH minus, two separate ions. So this is an ionic substance. When we mix them with water, the ions dissociate. So again, we say these ions have dissociated, they have separated in the water. Again, we can write an equation to describe this. We're starting with NaOH, which is a solid. And when we mix it with water, it's splitting to give us Na plus aqueous, AQ for aqueous, plus OH minus AQ for aqueous. Okay, so that's what's going on when we mix the sodium hydroxide with water and they dissociate. So what is it that's making it acidic? Well, it's these guys, the OH minus ions. So for something to be an alkali, it has to produce OH minus ions. So it's these excess OH minus ions dissolved in the water, that makes a substance alkaline. That is what makes a substance alkaline. And the same idea as before, some substances produce few OH minus ions. And these are less alkaline, whereas other substances produce more OH minus ions. These are more alkaline. All right, I think you're ready to answer some questions about alkalis now. Okay, so we've got the last two here. Okay, so from memory, list 2 common lab alkalis and then use a diagram like in question 5.
Sorry to interrupt you. Can I ask students and students please put up their chairs?
Sorry about that. It says use a diagram like in question 5 to describe an alkali. So just like I've done up there, describe an alkali using a diagram like what's in question 5. Okay, so pause the video and do those questions now. Right, so it should only be playing if you've answered the questions. 2 common lab alkalis. The options we have are sodium hydroxide, we could have, think of another metal in that group. We could have lithium hydroxide. Any metal in that group was going to make an alkali with hydroxide. The other one I gave you was potassium, which is also in the group with sodium. So potassium hydroxide. And another one is calcium hydroxide. Okay, and use a diagram like question 5 to describe an alkali. All right, so we've got to use, we've got to have a container. Inside the container should definitely be some water. And then in the water, if it's going to be an alkali, it's got to have OH minus ions dissolved. So that's not really, by itself, that's not really describing it. So this is water, and these are what we call hydroxide ions. So again, that's not really answering the question. We have used a diagram, but we haven't really described an alkali yet. How could we sum it up? Well, again, if you haven't done this, I would pause now and write a little summary of why this is an alkali. Pause the video and do it now. Okay, so why is it an alkali? Well, it's these excess hydroxide ions or OH minus ions make the substance alkaline. So again, without these hydroxide ions, these OH minus ions, if a substance cannot produce these, then it won't be an alkali. All right, so well done. If you've got that, if you've got those right up to now, you're ready now to do the next little task, which is what I want you to do is I want to pause the video, write this out, and fill in the blanks that you come across, please. Okay, so we'll do that now for me. Okay, so you should only be watching the video if you've finished this. All right, so answers are coming up. And again, if you haven't done this, you're not going to learn very much. You have to be practicing. All right, so here are the answers. So pause the video to make corrections now. Should make sense when you read through it with the answers. All right, we're just going to make this idea a little bit more complicated now. We're going to go back over here where we were describing these things. There's a little bit more to the story of acids and alkalis. So we're going to start with the acids. I haven't really given you a proper definition for it yet, and that's because there's a couple of definitions on the course. Now, we're going to focus very much on what we've already looked at, and we're going to look at one of the first definitions for acids and alkalis were like this. The first guy to figure out what was going on looks at this up here. The dissociation of chemicals to produce these H plus ions. He figured out that that's what made stuff acidic. Okay, his name was Arrhenius. Like this. That's what his name was, Arrhenius. And Arrhenius' definition of an acid was that it's a substance that dissociates in water to produce H plus ions, or hydrogen ions. So there's nothing new there, okay? That's what we've kind of already learned already. That acids are substances that dissociate when you put them in water, just like what we looked at up here. They split up and they produce these H plus ions. That is Arrhenius' definition of an acid, or an acid according to Arrhenius. He made the same type of definition about bases. So again, we've got this guy, Arrhenius. And Arrhenius' definition of an alkali was this. Can you guess what it is before I say it? Speak your answer to the screen, what you think it's going to be. Okay, what Arrhenius said was it's a substance that dissociates in water to produce not H plus ions, but OH minus ions, or hydroxide ions. So that was Arrhenius' definition of acids and alkalis. And it's pretty good. I have to say, even to this day, it still makes quite a lot of sense. And it's one of the definitions that they ask quite frequently on the exam. So certainly what I would advise you to do at this stage is to pause the video and take those down. So pause the video, take down the definition of the acid, do that now. Pause the video, take down Arrhenius' definition of a base. Okay, now a reminder that these are not the only definitions on the course. Let's take a look at what H plus ion is for a second. So what I want you to do is draw, you should all know how to do this, draw a Bohr atom of H plus. So think about that. What's happened for it to be H plus? Draw that for me now, please. Okay, you might struggle to draw this actually, because if you think about it, what is H plus? H plus, in the nucleus of a H plus, we've got 1 proton and 0 neutrons. Because hydrogen, if we look at the numbers for hydrogen on the periodic table, you've got hydrogen, it's got number 1 and 1. What does this mean? It means atomic number is 1 proton, but the mass number is 1, which means to get the number of neutrons, we do 1 minus 1, which is equal to 0. 0 neutrons. Now, normally, if it was an atom of hydrogen, we would have 1 electron, because remember, charges must balance, cancel out in an atom. But this is a H plus ion, which means it's now got 1 extra plus charge than it does a minus charge. So essentially, it has lost its 1 electron. So literally, all we've got in a H plus ion is a proton. There's no electrons. The 1 electron it did have has been lost. So H plus ion is just equal to 1 proton. Okay, with this in mind, this is going to lead into the second type of definition. The reason why there needed to be an updated definition of this was because Arrhenius' definitions fell short a little bit. And that's because not every alkali produces OH minus ions. Some alkalis can act like alkalis without producing OH minus ions. So the more updated definition of acids and bases comes from these two guys who came up with a new theory. And that was these people called Bronsted, Lowry. Bronsted and Lowry. And their idea or their theory and their explanation of an acid was an acid is a proton donor. Think about that word donor. That just means someone or something that gives away. So a donor like probably the word where we hear donor the most is like an organ donor. So an organ donor is someone who gives away the organ to help somebody else. Well, a chemical then that is an acid, according to Bronsted-Lowry, that is a proton donor. Now that should make sense, even when you mix it with Arrhenius, because Arrhenius says that you've got a substance producing H plus ions. Here they are. H plus ions are just protons. That's all they are. We just figured that one out. And they are producing them and giving them away. So an acid is a proton donor, according to Bronsted-Lowry. The single biggest thing students do in the exam is mix these two things up, these two definitions. So let's be clear on the difference between Bronsted-Lowry and Arrhenius. Bronsted-Lowry's definition of an alkali is probably more important than their definition of a base. And the reason for this is because Bronsted-Lowry's theory fixes Arrhenius's issues with alkalis. Arrhenius's issue with alkalis is that not every base produces OH minus ions. So it's not quite accurate to say that they produce OH minus ions. It's not bad because a lot of them do, but some of them do not. So what is a better definition then? Well, a better definition is that an alkali is a proton acceptor. So it's a substance that can take in a proton. Okay, it can suck up protons, can take them in. They can attach to the base, okay, or to the alkali. And we will see a little bit more detail on that later on, okay? So they are our definitions. Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. And know that this one here, Bronsted-Lowry theory, is the kind of more commonly accepted theory nowadays, even though Arrhenius's theory is still pretty good. All right, so let's now add our definitions of Bronsted-Lowry acid and base to your definitions that you took down for Arrhenius, and make sure you have them clearly distinguished. Which ones are Bronsted-Lowry, which ones are Arrhenius? Take them down now. There's the acid, and there is the Bronsted-Lowry base or alkali. Okay, so just to be clear, I am using the word base and alkali interchangeably. Now, it is a little bit more complicated than that, and there are slight differences in between what those two things are that we're not just going to go into it at the moment. I don't like to do that normally. I like to explain things and why, but it just doesn't suit to go into it right here. So just know that I'm using these words interchangeably, and you might see them in the exam interchangeably. You might be asked about a Bronsted-Lowry base instead of a Bronsted-Lowry alkali. Same thing, okay? All right, last set of questions. Let's have a look. Here. All right, so pausing the video, and from memory now, you got to close up your notes. See, can you remember these definitions? Okay, so pause the video and do it now. Okay, you should only be watching if you've got this done. Okay, so how does Arrhenius describe acids? Again, I think you can go back to your notes and check it instead of me writing it down. Go back and check Arrhenius's definition of an acid and Arrhenius's definition of a base. Do that now. Make sure you correct them or fix them. So they should have a tick mark, or they should be corrected if you got it wrong. H plus ion is literally like this. It's one proton. That's all it is, and it's positively charged. That's all it's there. There's nothing else there. There's no electron. There's no neutron. It's literally just one proton. Which particle is it the same as? Same as a proton. Well done if you got that right. And then how do Bronsted-Lowry describe acids? And that last one, sorry, that's clearly wrong. It's how do Bronsted-Lowry describe alkalis? So if you didn't write how they describe alkalis for the last one, pause the video and do that now. Okay, I think you can go back to your notes, what I asked you to take down, and check you have them right. Again, you should be able to do them from memory now. You shouldn't be relying and copying from your notes at this stage. All right, that's it for video 1 on acids and bases. Hopefully you now know what they are, you know how to describe them, you know how Arrhenius and Bronsted-Lowry both describe acids and bases. And that is it for today. I'll see you in the next one.